Hi everybody, welcome back. I apologize for the echo in this room. I'll do my best to fix that in editing, but we're going to get right back started on another fluid mechanics problem today. So I've gone ahead and written the equation we came up with last video. This is the Bernoulli's equation with all the components we want in it. And today we're going to be talking about an application of this equation on some tanks that will be draining. And we'll get more into this video. We're going to go over to the computer and do some coding and solve some more interesting problems, but we need to get a basis for where these equations are coming from before we start that. So today, I haven't written the question up on the board. We'll see that later, just because I want to get started first with something else. But we're going to talk about this case here. So we have a cylindrical tank, and it is draining out the bottom. And I want to represent this scenario with the equation that we have here in kind of simple forms. So what we're going to do first is define some things on our picture here. So we have a cylindrical tank. It has some cross-sectional area, right? And we're going to call that we'll call that big A1. Some cross-sectional area there. The water level is at some height, H1. Okay, and it's draining out of what we'll call H0 down here. Okay, and then we have to recognize that there is going to be a pressure at the top and bottom, and contrary to popular belief, both the pressures are the same. There's very little difference here. The reason being is because they're both exposed to the atmosphere at the top and the bottom. It's an open air tank in our situation, okay? So the pressure here, we'll still label, we'll give it pressure 2 and pressure 1. But they're both equal to atmospheric pressure, gauge pressure 0, okay? And then we have a flow, we have flow of water coming out of the tank, which can be described in terms of velocities and areas, right? So we've already defined the area here, but let's say there's some velocity, V1, and then there's also a cross-sectional area and velocity here. We'll use a little a. Actually, I'm going to use little a1 and velocity 2. Okay? And you'll see why I'm doing labeling it this way in a minute. I know it sounds strange, but okay, let's work on the application of this. So how do we represent this situation here? Let's say what we want to find first is the velocity of the water draining out of the tank. So how fast is that water flowing out there? Well, first of all, we can pretty much ignore this side of the equation, right? We're not adding any additional non-flow related work or heat or energy to the system. So I'm just going to go ahead and cancel all of these out. They're all 0 in this situation. It's just simply draining out a hole. Additionally, we said the pressure at the top and the pressure at the bottom are the same, meaning P2 minus P1 is going to be 0. Okay? And so what we're left with is these two terms. We obviously have a change in height of the fluid, and then we obviously have a change in velocity of the fluid. It's going to come out faster at the bottom than it moves down the top. For the purposes of this exercise, we're going to say that the hole at the bottom is so significantly smaller than the large cross-sectional area at the top that the velocity of the water moving down through the tank is negligible compared to the water flowing out of the tank. So we're going to call V1 specifically 0. Okay. With that being said, I think we can take these equations and move forward. So we have H2, and I guess I used slightly different numbering here. I'm going to transfer this over. So this would be like H1 and this would be H2. Okay. Okay, so we have H2 minus H1. In this situation, we're going to just say H1 is at the 0 axis, right? it's at 0. So we basically just have, let's see, how do I want to do this? No, we're going to do this differently. So we'll say that instead, I'm going to come up with better numbers for this. The water is moving from H1 to H2. I think that's better. Do you guys agree? It's moving from H1 to H2. So yeah. Moving from H1 to H2. Okay, that works. So we have H2 minus H1. Okay, if H2 is practically at the 0 level, we'll kind of see that go away here in just a second. So we're left with this, right? Okay, and we said this was going to be 0. So now we have H1 times G, and then I'll just move this over to the other side. V2 squared over 2. Okay, and look at that, we're really close already to solving for V2. This is actually a pretty simple problem. Move the 2 over and then take a square root, and we're left with V2 equals the square root of 2 times H1G. Okay, that's really simple. Now, let's make the, before we make it a little bit more complicated, let's talk about flow. Okay, so there's a velocity of the water coming out, but that only describes the velocity, not the actual volumetric flow of the water, right? So flow Q, we'll call it Q1, is equal to V times A. And we use the little a to denote the cross-sectional area of the water coming out, right? So we have, I guess sorry the numbers are a little bit funky, but we have V2 there and little a1. Okay, so that would mean our Q for tank here is radical 2GH1 times A1. Okay, I'm happy with that. So let's make this a little bit more complicated now, and this is where the real problem is going to come in. So we have one tank in this situation. Let's move to a scenario where we might have a series of tanks. They're not connected by anything, any hoses, they're just simply spilling into one another, okay? And then there's an initial flow going into the first tank, okay? Something like that. And so we call this flow here Q1, right? We just denoted it as Q1. Should make this one Q2. And I'll just call this one Q in, okay? And then we described the hole here at the bottom of the first tank as little a1, which makes this one little a2. Similarly, we have a cross-sectional area of this tank of big A1, a cross-sectional area of this tank is big A2, and a cross-sectional area of this tank is big A3. Okay? And now here's what's going to be interesting about this problem. Let's say we have some initial height of water in all of these, okay? And we want to raise the height of the water in the very last tank by controlling the flow in the inlet. So maybe it's like a fish tank or something like that, one of those like waterfall cascade fish tanks or something. And we want to raise the water level in the third tank. So how would you go about doing that by changing the flow rate of the first one? Well, we have to come up with an expression that relates the height of the water in this tank to the flow of the inlet, right? So let's talk about how you might do this with a digital controller. Okay, so first of all, let's define, maybe we want the height of the water to be at some set point. So I'll say the height, or let's do, yeah, so we're going to say like the error, which is going to be the difference between where we want the water to be in the third tank and where it is now, is going to be equal to the height of whatever set point we want minus the height in the third tank, the height of the fluid in the third tank. Okay, so how do we go about minimizing this error between the set point and where the height of the water actually is based on the flow in the first tank? Well, you can say this is how a controller works, by the way. You have the Q in is going to be equal to whatever you started with as the Q in, so we'll call it Q in naught, plus a constant which acts as a controller gain, we'll call it KC, times the error. Okay? And this is kind of like this iterative process where you keep plugging in until you get the right spot. Okay? And so we have one more expression that we need to define here. We have the this is kind of where it all comes together. We have the rate of change of volume, right? That is what flow is essentially. The rate of change of volume in these tanks. So volume, if you remember, is the cross-sectional area. Let's do this for the first tank. So the rate of change of volume in the first tank is described by the rate of change of area times height, right? Volume with respect to time. And this just equals our Q in minus Q1, right? So we have something going in, something going out. That's the rate of change of volume. Okay, but we already said that Q1 is equal to this expression. So we can plug this in to tie it all together here. We get Q in minus radical 2G H1 A1. One other thing here is we see that in this little expression here, I described the rate of change of volume as the rate of change of area times height. But the only thing that's really changing with respect to time here is height. The area is not changing. The cross-sectional area of the tank remains constant as the fluid level decreases. So we can really take this out and divide it across. What we get is the rate of change of height. And this is what we really want, because we can do this for each tank. I'm just doing it for the first one. We can do this for each tank. We have the rate of change of height in the first tank is 1 over big A1, took that out, remember, times the inlet flow minus the outlet flow. Okay? So now we have an expression that describes the rate of change of height in the first tank with relation to the inlet flow. What we can do now is write that expression for each tank, okay? And then solve them all at once, which that's where we're going to go to the computer and use this for. So let's go ahead and write these expressions before we head over to the computer. So we have, this is for the first tank. If we were to do the same for the second tank, it would look like this. We have, I'm just going to write them up here. We have the rate of change of height in the second tank with respect to time is equal to 1 over the area of the second tank times the inlet flow. Well, what is the inlet flow of the second tank? It's the same as the outlet flow of the first tank, which is this. So we have 2GH1A1 minus, what is the outlet flow? Well, it just follows the same pattern as what we just went through before, right? So we have 2G, we'll say we're going to call, when I write H2 here, I'm not talking about H2 in our original problem, I'm talking about tank 2, okay? H2A2. Okay? And the rate of change of flow for the final tank, or excuse me, the rate of change of volume for the final tank, same format here, 1 over A3 times what goes into A3, which is the outlet from tank 2, 2GH2A2, then minus what goes out. So let's just, maybe we can assume that this tank also drains into the atmosphere or something and has a cross-section of a whole A3. Okay, so same thing here. Okay. And now we've written all three of these expressions for the rate of change of volume of each tank. The rate of change of volume for each tank, described by the rate of change of height in each tank, right? Okay, so what do we do with these? Well, we can put some numbers to these equations, like let's say we wanted to raise the height of the water in the tank by, I don't know, X number of meters. Well, we can go in and we can solve all of these backwards so that they all solve at once, and that's exactly what we're going to do. So stay with me and join me back on the computer here in just a second, and we're going to put some numbers to this problem. All right? Okay, thanks for joining me back on the computer. We're going to get started chugging away at this problem real quick. So we've kind of come up with the differential equations that we need to model a problem like this, and now what we want to do is put some numbers to that problem and make it a real life example. So I've got you on the screen in front of me, I'm sharing my screen, and then I've got you behind me as well. Let's go ahead and put some numbers to this problem and see what we got. So there are three open air tanks with cross-sectional areas of 1.52 and 2.5 square meters respectively. Okay, so the tanks get larger as they drain into each other. The drain from the bottom of each tank, an area of 0.01 square meter, exits into the atmosphere and gets collected into a subsequent tank or to the atmosphere for the final tank. Okay, just like we drew in our last example. The inlet to the first tank, we call that Q in naught, is 0.03 cubic meters per second, and that's been maintained for a long time. It was in a steady state. It's suddenly increased by 10%. Okay, derive and solve the set of differential equations using scipy.integrate.solve IPP and plot how the height changes. Okay, so we're interested in how the height of each tank changes with respect to time, which are those differential equations that we came up with last time. And remember, we got to those differential equations for the change in height with respect to time by finding the differential equation really for volume with respect to time, and then knowing that the area of those holes in the tanks don't change, we can get rid of area and we're left with height. Okay, so let's go ahead and import all of our things we're going to need to solve this. So I'm going to import numpy. Okay, we're going to need import solve IVP. Okay, and I believe, yeah, we're going to make a plot of this at the end. So let's do from plotly import make subplots. Let's see if that works. Uh-oh. I don't remember the name of the plotly thing. Let's see if we can look it up really quick. Plotly plots. From plotly dot subplots. Import make subplots. I think that's what we need. From plotly dot subplots. Import make subplots. That work? Okay. Let's chug away now. We've got so we're going to need to import all the things in the problem, and then we'll kind of work in the things that we derived on the whiteboard from last time. So the first thing we obviously need, we're going to need the value for gravity, 9.81. That's in meters per second. Let's see. So they give us the cross-sectional areas. I believe we used capital A for these areas. So the cross-section of tank 1 is 1.5. Okay, and that's in meters squared. A2 is 2. and a 3, we have 2.5. Okay, then we know that the hole in the bottom of each tank has a cross-sectional area of 0.01 meters squared. So we can say that little a1 equals, those are the same for all of them. Okay. All right. So I think we'll start with that. Now, we need to express somehow the initial height of each tank. We know that the flow in that Q, oh, that's the other thing we need. I forgot. Q in naught is 0.03, and that's in meters cubed per second. Okay, so like I was saying, we need to kind of write an expression here. We need to define what the initial height of the fluid in each of these tanks was. We're not given a specific height, but we do know that the system was in a steady state, and we can use that expression that we came up with for flow. It would have been Q equals radical 2gh times the cross-sectional area, like little a. We can use that kind of working backwards and with the initial flow to write the initial height of each tank, of the initial height of the fluid in each tank. So we can call this like H1 naught, for example, and this is going to equal, okay, let's see. If we had Q is equal to radical 2g H1 times A1, and we're solving for H1, we would need to divide by A1, Q divided by A1, right? So we have the Q in naught divided by, see, that would have been A1, right? Divided by A1, okay? We would need to then square this quantity before dividing again by G and 2, right? So we just work backwards there to get this expression for the initial height of the fluid in tank 1. We'll need this for each tank, so I guess I'll just retype it. H2 naught is equal to, we have Q in over Q in naught over A2 squared divided by 2G. And then lastly, H3 naught, Q in naught spelling. Okay, great. So we now have an expression for the initial height. And now we have to kind of tell the program here that we want to change the initial flow. And that's how we're going to get the new heights. Okay. Okay, so now we need to define our set point. For the height of tank 3, it's going to be equal to 1.1 times H3 naught. Right? Increase by 10%. Then we want to, it's typing what I was saying. Then we want to define a controller gain. We talked about this, how the controller works, 0.25. Okay, now we can define our function that we're going to solve with IVP, with the solve IVP command. So let's define um, a function. I'll call it just, well, maybe not f. Let's call it like right hand side, I guess. Um, okay, calling it right hand side. And then we need to define, the reason I put V here, it stands for vector. We need to define what H1, H2, and H3 are as they're changing. So that's going to be this vector here. So we have H1, comma, H2, H3 equals V. Okay. And then remember we have an error that exists between our set point and what the current state of H3 is. That's what the controller then sees and then adjusts to. It says error. So our error is going to be the set point for H3 minus what H3 actually is. And then what happens is Q in is going to equal the flow that's changing, right? Is going to be equal to Q in naught plus the controller gain times the error. Okay, just keep it. Okay, great. Now, what we can do is write in our equations for flow, right? So we're gonna have Q1 equals something, we'll have Q2 equals something, and Q3 equals something. We already did this. This is just our square root of 2GH um, times the area of the hole, right? And all we're going to do is we're going to write these equations for the flow, and then we're going to output the differential equations that or that we're going to return the differential equations that we came up with, remember, which is like the first flow minus the second one divided by the area of the first tank, something like that. We had 3 of those equations, so we'll transfer those in here as well. But for starters, we had Q1, that's going to be equal to MP dot square root, not comma, dot square root of 2 times G times H1. Okay. And then that was times the cross-sectional area of, oh no, I apologize. It was equal to the area of the hole in the bottom of the tank, yes, times A1. Okay. We have this again for the second tank. And again for the third. Okay, and we're going to want to return an array of those differential equations. Okay, so what were our differential equations? What the differential equations described was um, it was the change in height with respect to time of a tank was equal to the flow of the first tank minus the flow into the second tank divided by the area of the second tank, right? So we can show that here, or excuse me, the area of the first tank. We can show that here as it would be, we're gonna want these guys in here. our first one's going to be Qn not. We want Qn or Qn not here. We want Qn minus Q1 divided by A1. Okay, and that's a little bit confusing. I'm using big A there, right? That's the cross-sectional area of the actual tank. Okay, and then we have it again for Q1 minus 2 divided by A2. And lastly, Q2 minus Q3 divided by A3. Okay, I think that's looking right. So that's the array we're going to return, and then use solve IVP to solve. Okay, let's start a new line here. So after we return this array, we're going to get our result from solve IVP. Already imported it. Okay, we need, if you can see here on the screen, we have the, we're gonna need to define the function, the span of time, the initial conditions, and then some method for solution. Okay, so our function is, we defined it as RHS. Okay. Our time period, oh, okay, we forgot one thing. What is our time period? Let's go from 0 to some time end, we'll say 5,000 seconds or something like that. Okay, so we need to go now from 0 to 5,000 seconds. Next was the initial conditions, which is going to be H1 naught, H2 naught, and H3 naught. So I'm going to put in an array here of those. Okay. And then we need a solution method. I was advised to use the Rideau method, so we're going to use that. Okay, let's see if this works. Great. Okay, now we have our result, our solution. We should be able to go ahead and start plotting this. One more thing I forgot here was to write dense output equals true. Okay. Okay, so now we can start plotting. So we need a t-plot is equal to np dot linspace. We have 0 to t end. We're going to do, I guess, 1,000 increments. And then we have equals our result, solution, and then t-plot. Yeah. Okay, so we have those in there. And okay. Now we can do our subplots. Bigger. Where we've imported our make subplots from Plotly. figure dot add underscore scatter. There we go. Okay, on the x-axis, we're going to want our time, our plot of time, right? So we just made a like a linear space for time, right? 1,000 increments. And then, so that's where we want our x-axis. On our y-axis, we're going to want the height of, say, tank 1, right? And we'll say the name of this is tank 1. We need to do this. Let's do it for every tank. So we have now add underscore scatter. Two. And the name of this one, 2. Last but not least, y equals h3 and name equals tank 3. Oh no, I made these all goofy. Make it uniform just for my own sake. Okay. Let's see what this looks like. All right, we can fix that. There's nothing wrong with it, probably. We're just zoomed way out. Let me auto scale this or something. Anyways, let's see if we can fix this. It's fig dot update layout. Yeah. To width equals 800. Split. Dark, I think. Let's try that. Okay. So it looks like we may have made an error somewhere. Let's go back through and see where this error could possibly be. Okay, so it looks like I found the error. At the very, very beginning, I made an error here. We were given that the area of the drain in the bottom of each tank is 0.01 square meters, and I made the mistake of 0.1 square meters. That's going to throw our answer off quite a bit. So let's rerun this back. Okay, that looks a lot better. So what do we have here? We have a plot showing the variance in fluid height in each tank. You can see tank 1 in blue, tank 2 in red, tank 3 in green over time. And what this is showing, the waviness here, that's the controller adjusting for its own error. So it slowly, it overcorrects and then it comes back. And it overcorrects the other way and it overcorrects again. But as you can see, it is going to diverge on the final changes. Okay, so I think we've completed our problem now. We have used scipy.integrate.solve_IVP to derive and solve the set of differential equations, and we've plotted how the height changes over time. So I think we are good. Thanks for joining me on this video, and I'll see you again shortly here for the next homework.